Hey, welcome back to Bennett's Chemistry 12 tutorials. Today we are moving on in our titration unit, and we are on to titration curves, and kind of the next step in I guess the complexity of titration curves is to take a look at strong weak combinations. Okay, so in the previous video we did strong titration curves. Where you were taking a strong acid and titrating with a strong base, or a strong base and titrating with a strong acid. Doesn't matter which goes where. The graph would have similar characteristics, except they would start at a different pH. So we learned last class, when you're titrating a strong acid with a strong base, the pH started low, and depending on what the acid concentration was, and as you were adding the base, the pH rose a little, but not terribly fast. Went up and went up and went up. And then once you got really close to the equivalence, it rose really sharply and went shooting up all the way above pH of 7, all the way near like 10, 11, 12, and then plateaued out and carried on almost. It had like this very typical cobra-looking shape. What was very identifying about the fact that you were titrating a strong acid with a strong base was that the equivalence point, so the middle of that really steep rise in the titration curve, was at a pH of 7, because the pH at equivalence for a strong titration is pH of 7. Now, if we started with a strong base and we were titrating with a strong acid, it would have started high. pH would have started high. It would have gone lower and lower and lower and lower, very slowly, and then, and then it would have dropped rapidly and gone down into the acidic range really quickly. Again, the middle of that steep section would have been at pH 7, because it's still a strong titration, and so therefore the equivalence would have occurred at pH 7. And it's a very identifying feature of a titration curve that is of a strong combination, in that the equivalence point, the middle of the steep section, is at a pH of 7, and that's how you kind of identify what you're titrating when you're using a curve. You can also use that curve, and knowing the equivalence is at 7, to read off what volume of your titrant was required to actually reach equivalence. Okay, so that was strong. Now today we're going to get into the strong-weak combinations. There is some similarities between the two of them, obviously. We're still doing titration. We're still talking about acids and bases. But there are some very unique identifying features of this type of titration curve that will help you identify things and actually come up with some numerical answers for some things. So I thought the best way of doing this would just be to do an example. It was like a little case study here, because although you might get some subtle differences in terms of what the actual numbers might be, the shape of the curve, some of the features that you're going to see in the titration curve will be similar. Okay, and so you can use this one case study that I'm about to do, and you can then apply the general shape of things to any strong-weak combination. Okay? Before I go any further, though, next video will be on titrations of di and triprotic acids and bases, okay? And they have, again, another unique identifying feature. Okay, so that'll be next class. Okay, so my example, and I've put it up here on the board. My example is going to be, I'm taking a sample of acetic acid, so CH3COOH. And I'm taking that acetic acid, and it's a 10 ml sample. And I'm going to titrate with sodium hydroxide, which is a strong base. So the acetic acid is a weak acid, and sodium hydroxide is a strong base. Okay, so that's our combination. Now, I mean, if you were actually doing a titration, you would probably not know the concentration of the acetic acid, or maybe you don't even know it's acetic acid. You would just know it's some acidic solution. But because I'm trying to show you what the curve looks like here, I'm going to use exact values as if I know everything, and then I'm going to go through and I'm going to describe what you're going to see. Now, the reason why I did this is because I've actually pre-calculated some of the critical points on this titration curve, in terms of the volume of base added and the pH of the solution that you would have at any moment in time, so that you can actually see some of the unique features of this type of a graph. Okay, so I'm taking a 10 ml sample of 0.2 molar acetic acid, and I'm titrating with 0.2 molar of sodium hydroxide. Now I chose those numbers for a very specific reason, and because they're the same concentration, and the neutralization equation, there's acetic acid, there's sodium hydroxide, because the neutralization is 1-to-1, and the sodium hydroxide forces this reaction to go 100% towards the products, that if the acid concentration was 0.2 and the base concentration is 0.2, then they are going to require equal volumes to hit the equivalence point. Okay, so I did that on purpose so that the math doesn't get all kind of crazy in there. So you can already guess that a 10 ml sample of 0.2 molar acetic acid is going to require 10 mils of 0.2 molar sodium hydroxide to reach equivalence. So we already know when I come over here to my volume of base added, that at 10 milliliters, that's where my equivalence point is going to be. Okay, it's going to be at that volume right there. But there's some other kind of unique features along the way that we need to get into. Okay, quickly, just I'm going to show you this picture that I've drawn here just to give you a sense of what this titration would look like. Down in the Erlenmeyer flask, we would have the acetic acid, the 10 ml sample that we've pipetted. We would have put an indicator in just because you typically do. Again, if you were doing a titration curve, you'd have a pH probe in there to be measuring the actual pH. So I guess it's not necessary to have the phenolphthalein, but oftentimes you do, just so you know kind of when you've hit equivalence, so you know when you can stop. So that would be down here, and then up in the burette is where the sodium hydroxide would be, and we'd be adding it. Because we're doing a titration curve, you'd probably be adding it at, I don't know, half mil increments or something like that. Okay, so that's that, and I've pre-drawn the axes for my graph. Okay, so I've got the pH over here, and I've got from 0 all the way, I guess I could have put up to 14, I stopped at 13. I know what the numbers are, so 13 was high enough. And then the volume along here, I've got increments for every milliliter. Okay, now I've only written down the even ones along the way, but every milliliter, there's an increment there. Okay, so I haven't got a perfect graph paper or anything like that. It's a whiteboard. So I'm going to try my best to plot these points. Okay, so what things do we know numerically? Well, before we even started doing the titration, right, we haven't added a speck of sodium hydroxide. The acetic acid, 0.2 molar, would be floating around in its 10 mils, doing its equilibrium, right? Like, who cares that you're doing a titration? It's an acid, so it's doing its weak acid deal in the water. So it's doing this, right? Like, this is the equilibrium that it's doing. It's producing hydronium, and it has an equilibrium constant as a Ka. Let's pretend we're doing this at 25 degrees, so we know what that number is. And we can solve for the hydronium because we know what the Ka is and we know how to do all of that. Go back to the weak acid stuff. So I've done that. So I've done the initial pH. And the initial pH of this solution before we even start the titration is 2.72. So at 0 mils of NaOH added, the pH is 2.72. So I'll use a red pen. 2.72. So it's going to be right about there. And now, just so you can see it, I'm going to use a little X. I wouldn't normally I'd use the crosshairs things typically, but I'm going to do the X so you can really see it as I draw this thing along the way. Okay, so that would be its initial pH. That was at 2.72. I'm showing you the curve, so I guess the actual number doesn't actually matter. So 2.72. And that's just what the pH probe would be showing. Remember, I've done the math, but you're actually getting these values from a pH probe as you do this titration. Okay, the other one that we know right off the bat is at equivalence. Okay, so let's think about equivalence. So I've already kind of talked about this. So 10 ml sample of 0.2 acetic, because it's 1-to-1 in the neutralization, will require 10 milliliters of NaOH. So at 10 mils added here, I'm going to have my pH at equivalence. Now, because I know the number, I've done the math. Now, the math it's not super hard. I mean, I'm sure you've got the skills to be able to do this. This is how I did it, okay, just in case. Maybe you've got a teacher who actually asked you to do this. So because this is the neutralization reaction, what I did is I calculated how many moles of sodium acetate get made. Because I know at equivalence, the pH at equivalence is going to be due to the products. Well, the water is water, so it's part of the solution. NaCH3, COO. That sodium acetate is going to be the chemical that makes the pH other than 7. So I need to know the concentration of this thing before I can actually do any of the math. So what I did is I figured out how many moles of this thing did I have originally. So I did 0.2 moles per liter times how many liters I had times 0.0100 liters. Got the moles. I then divided by the total volume that was going to be present at equivalence. So it's not 10 mils, right? If you can imagine during the titration, 10 mils, you've added 10 mils. The total volume is now 20. So I took the moles of this thing that I expected to produce, divided by the total volume, and that's the concentration of the acetate. Acetate is a base. So then, using its Kb, I calculated what the pH would be of that concentration of acetate. Okay, and so I did this all pen and paper kind of thinking along the way. So, long story short, the pH at equivalence, when you do all of that math, comes out to 8.87. So at 10 milliliters here, the pH comes out to 8.87, which is right about, let's see if I can get this right, right about there. Okay, so 10 milliliters of base, okay, and 8.87, just below the 9. Okay, now did I maybe put that a little bit high? That looks a little high to me. I think that's a little bit better. Okay, so it's right about there. Okay, what else do we know? Well, you don't know really anything. So what you're doing is you're doing the titration. It starts here, maybe at every half a mil you'd stop and measure the pH and you'd start going ahead and doing it. You know that at equivalence it's going to be here because the pH at equivalence for a weak acid titration is going to be above 7. It's not going to be neutral because you've made sodium acetate, it's a base. So that's expected over here. That will be, okay, keeping in mind kind of some of the things we know about titration curves in general. That will be the middle of the steep section as the pH changes rapidly. That's going to be the middle of that steep slope. Okay, so let's keep that in mind. So here's some other math that I did. So I did the math after the equivalence. So you get to equivalence, you've made this solution. Okay, great. If you keep adding sodium hydroxide, you add another mil of sodium hydroxide, then another mil of sodium hydroxide. I calculated those pHs as well. So 1 extra milliliter of sodium hydroxide added into the 20 mils that was already there, so now your total volume is 21 mils, you essentially have a slightly diluted solution of the sodium hydroxide. And so I did the pH of that. I calculated the pH of that. And the pH, after 1 mil too much of the sodium hydroxide, goes all the way up to 11.98. So at 11, it's 11.98. It's about there. I then did 12. So another mil, and you calculate the pH again. Your pH meter would be telling you what this is, and it's 12.26. So 12.26. So you can kind of see how Like this is going to be, that equivalence point pH is going to be the middle of the steep zone. But as it goes shooting up, what will happen is it will kind of start to curve a little bit and it will eventually plateau. Okay, and you see that very typically, not typically, very typically, you see it always on a titration curve, is at the end you get this rapid change in pH and then it plateaus and it kind of plateaus forever kind of thing. Okay, it doesn't matter how much you add, it's just going to plateau. Okay, so those are kind of after the equivalence point. What about before the equivalence point? What about between the initial pH and the actual equivalence? It gets a little trickier because weak acids are an unusual beast in that as you're doing the titration, okay, so as you're doing the titration, you're doing this neutralization reaction, okay? And when you're doing this neutralization reaction, you are essentially taking this molecule here and forcing it, whether it likes it or not, whether the equilibrium down here likes it or not, you're forcing it into its conjugate. Okay, 100%, you're making it do it. Now, what that means is you're messing with this K expression, like you're messing with the concentrations in that K expression. And you are, during the titration, you are manipulating these things. Okay, so that's the first thing to understand. What you're doing is, in this equilibrium, you are decreasing what's over on this side and you're increasing what's over on this side. What that creates is what's known as a buffer solution. And buffer solutions, you have to understand what a buffer solution is in order to get what's happening in between the initial and the equivalence of these titrations. So a buffer solution is one that resists the change in a pH with the addition of acid or base. Okay, so addition of hydronium or hydroxide. So resists change to pH. It doesn't prevent changes in pH. Like the change will still happen. It just minimizes it. And the reason why it minimizes, why a buffer solution minimizes the change in pH is because this equilibrium that's here, if you have large concentrations relative to each other of the acid and its conjugate base in this equilibrium, so you've got lots of this and you've got lots of this relative to each other, that thing has equal ability to shift. So if somehow you alter this variable, okay, you alter the hydronium concentration, either up or down, you can the equilibrium will shift to adjust for that change in the hydronium concentration. Now, as a result of that, kind of long story short, as a result of that, it will shift to adjust and resist the change in that hydronium concentration. So if at equilibrium, if you decrease the hydronium, the equilibrium can shift that way to replace it. And so the hydronium doesn't stay exactly the same, but comes back close to what it was previously. If I increase the hydronium, then it'll shift that way to get rid of it. And so even if you've added it, it will shift away and reduce that hydronium. Again, not exactly what it was before, but close to it. Buffers have this ability to resist changes to pH. Now, what is so unusual about the titration of a weak substance is that as you're doing the titration between the initial and the equivalence, is you are creating a buffer solution. You're actually forcing this into this, and you're creating a solution that has high amounts of the acid and its conjugate. You are creating a buffer. And so therefore, there's a resistance for the change in the pH. That's kind of an unusual, weird thing. Now, in order to calculate the pH, anywhere along the way here, what I had to do is I had to use what's called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is essentially taking the equilibrium expression for your weak acid. In this case, it was acetic acid. And what you do is you manipulate it a little bit in terms of its mathematics, and then you take the negative log of both sides. So essentially, if I take the negative log of the left-hand side, I get pKa. pKa of the acid. In this case, it was acetic acid. So if you take the negative log of the Ka of acetic acid, 1.8 times 10 to the negative 5 is its Ka at 25 degrees. You negative log that, and you get 4.74. So that's what the pKa of acetic acid is 4.74 at 25 degrees. If I take the negative log of this, it's kind of an interesting thing because you use your log rules and you can separate some things. Essentially, you can take the negative log of the hydronium, and if you take negative log of hydronium, that's pH. And then, see that little part right there? It's almost like the negative log of the hydronium times the acetate over acetic acid. And so if you use your log rules, essentially, if you remember, log of two things multiplied together is the same as the sum of the individual logs. So there's the negative log of the hydronium, and then negative log of plus the negative log of this thing. So plus the negative log of that. Now, kind of, again, mathematical manipulation to get it kind of where it's supposed to be. Again, knowing your logs, the actual equation oops, I'm using the exact thing. Okay, so what I did is I took this term, and because there was a negative sign out front, that became an exponent, which meant I could flip it and make it the inverse, and so it becomes plus log of the acid over the base. So essentially, the pH of any solution, okay? So the pH of any solution can be solved if you know the Ka and you know the ratio of the acid to the base concentrations. Okay, you know this ratio. Well, as I'm progressing through this titration, so as I'm going from here to here, what you're essentially doing is you're altering the ratio of this and this because you're forcing the reaction to go. So you start with almost all of this and almost none of that. And then this starts to get whittled away and it goes down and down and down and down. This starts to go up and up and up and up and up. And so I just said to myself, okay, so after X number of milliliters of sodium hydroxide, how much of this has been reacted, how much of this has been produced? And so I then took those ratios, or those concentrations, put them into this ratio, and then solved for what the pH of the solution would be. Okay, so the Henderson-Hasselbalch and doing all of this is not really part of Chem 12, but I'm just describing how I arrived at these values. So when I did this math, the first number that I did is after 1 ml of sodium hydroxide added. Okay, so we've just added 1 ml, like I'm right here. What's the pH of that solution? After only 1 milliliter of sodium hydroxide, the pH rises pretty darn quickly, up to 3.79. So it starts here at 2.72, and then it rises to 3.79, which is kind of kind of interesting. I mean, look at the trajectory it's going. Like it's like shooting, way up there if you continue that on a straight line. Like it's rising very quickly, way more quickly than you would ever anticipate. And that's very typical of a strong, weak titration, is that the change in pH, like in the first milliliter, is usually a significant change. Like it changes quite dramatically. Okay, so that goes up pretty darn quickly. But then what I did is I calculated the pH at 5 milliliters. And at 5 milliliters, okay, let's see if you can get this one. At 5 milliliters, that is exactly halfway to equivalence. So 10 mils was equivalence. Halfway at 5 milliliters of base, halfway, that means I've taken half of this and converted it into that. Logically, mathematically, that means the amount of this remaining equals the amount of that that's been added. This ratio in the Henderson-Hasselbalch equation is 1. The acid to base ratio, because they're the same concentration, is 1. The log of 1 is 0. Which means that when you get to halfway to equivalence of a weak titration, a strong weak titration, halfway to equivalence, the pKa will equal, the pKa of the acid will equal the pH of the solution. Kind of an interesting thing. That pH for this guy is 4.74. So at 5 milliliters, it's 4.74. It's doing some interesting things here. It went up very rapidly, and then it obviously bent and kind of came back along here. And now now it's obviously got to turn back up because we got to get up here to the equivalence one. I also then did, well, when it's 1 milliliter from the equivalent, so after 9 mils of sodium hydroxide, I did the exact same thing. I calculated how much of this is remaining, how much of this has been produced. And when you plug those numbers into the Henderson-Hasselbalch equation, you get 5.69. 5.69. At 9 mils, it's 5.69. This is, I mean, it's really quite interesting that it's rapid, then it plateaus off, and then it's still kind of plateauing almost. It must be curving, and then it shoots, and there you go. So when I actually draw the curve, you're going to see this plateauing effect. Then you're going to see a rapid rise. And then it's going to plateau off. Okay? So using this guy as an example, using the acetic acid as an example, there are some really important things to understand, to visualize in this type of curve. And I'm going to write them down. I'm going to write down the points because there's 2 critical points. Okay? So critical point number 1. Now, I'm just using the very generalized not equal to 7. I titrated a weak acid, and so therefore the equivalence point was above 7. If I titrated a weak base, then you take this curve and you kind of flip it upside down. It would have started up higher, it would have plateaued, and then it would have dropped, and the equivalence at pH would have been below 7 if it was a weak base being titrated with a strong acid. Okay, so I just said not equal to 7. Already, you should be able to identify the difference between a strong titration and a strong, weak titration. What is the pH at equivalence? Strong, the pH is right on 7. Strong, weak, the pH is not 7. Okay, so that's like the number one thing you look for is you look for that. The other thing that you're going to see, sometimes it's really obvious, sometimes it's not so obvious, is what's known as a buffer zone. That plateau in between the initial pH of the solution and when you arrive at the equivalence point. Okay, now it's that plateauing effect. So you see this initial change, the rapid change. Again, if I started with a base, it would have been a rapid change downwards, and then it would have plateaued. Here we've got a rapid change upwards, and then it plateaus. It's the plateau is visually telling you a resistance to a change in pH, because in this whole section in here, you're adding really strong base, like you're adding sodium hydroxide. It should be changing more rapidly than it is in this section. But because you've created a buffer solution, it is almost like a sponge. It's absorbing that base, and it's not allowing the pH to change so dramatically at that moment in time. So this is kind of what happens right at the very beginning, right, where it changed really rapidly. You don't have very much of this acetate in the equilibrium, and so it's not doing a very good job of resisting change to pH. You add a little bit more, like you carry on into the titration a little bit further, you make more of that acetate, you create a ratio that's a little bit getting closer to 1:1. And so therefore the solution begins to get better at absorbing the base and resisting changes to pH. It's the very flattest when the ratio is 1:1. It has the best ability to absorb any additional acetate or base. And so the flattest section is the middle of the buffer zone. The middle of the buffer zone is always halfway to equivalence. And it's always whatever the pH is at that moment in time. So right here, that guy right there, that's pH equals pKa. Okay? As you continue in the titration, you add more and more base, you eventually start to run out of this, run out of the actual acid. So as you're getting closer to equivalence, you're losing some acid. You're altering this ratio so much that the solution's starting to lose its buffering capacity. And so because it's losing its buffering capacity, it starts to change pH a little bit more dramatically. And then all of a sudden you lose all your buffering capacity, and boom, you go to equivalence and we're done, type of thing. Okay? And so those are two features that are really common in your strong, weak. The one that is absolutely 100% identifying is this pH is not at 7. This sometimes doesn't quite look as dramatic as what I've drawn on the board here. I happen to have used an example where it was going to be quite dramatic in what you can visualize. Sometimes it's not quite that way, okay, depending on what the acid is, what your starting concentration was, what the initial pH was, a whole bunch of other things. Okay, so it's not necessarily going to be, boom, it's obvious, there's the buffer zone type of thing. But this will definitely be there, okay? Now, those are the two kind of key things. If I had a base, I'm just going to draw it just roughly up here. If I happen to be doing a base, okay, so let's pretend I was titrating a weak base. So the pH might start up here somewhere. Okay, somewhere above 7. It would have an initial drop probably. It would have a plateau, which would be your buffer section. It would then start to lose its buffering capacity and it would drop. And then it would go down there. The middle of the steep section. So about there is the steep section. So the middle of it would be about right there. And clearly that is below. So here's pH of 7. Right? Clearly, that middle of that steep section is below 7. So therefore, this would be a weak base solution that was being titrated with a strong acid. What would it have looked like if it was a strong base? Well, the strong base would have, it could even start at the same pH. Chances are, if you have a strong base, it's going to be a slightly higher pH than that. Maybe it's going to be up here. It might go along. You don't see that rapid change right at the beginning. There's no buffering effect because there's no equilibrium in a strong base. And then what will happen is it will drop. And when it drops, it'll drop quickly. And the middle of that steep section will be right at pH of 7. Okay? And so you can identify the blue line would have been a strong base being titrated with a strong acid. The green line would have been a weak base being titrated with a strong acid. Okay? So there was quite a bit of detail in there. Remember that the identifying feature, there are 2 key features of the strong-weak titration curve. Number 1, and the one you gotta know, is that the pH the pH at equivalence is not going to be at 7. So the middle of that steep section is going to be either above 7 or below 7, one of the two, depending on what the solution was you were titrating. The second feature is the presence of the buffer zone. Okay, so halfway to equivalence, halfway to the steep section, you're going to see a plateauing effect. May or may not be super obvious or super dramatic, but if you've got a weak acid or a weak base being titrated, it will more than likely be there. Okay, so next time we're going to see for polyprotic acids and what do those curves look like? How can you use them to help you identify your unknown? And that will be our last class on titration. And then once we're done titration, we move on to the reduction oxidation unit, which is always the final unit in chemistry 12. Okay, so we'll see you then for polyprotic acids and polyprotic bases and their titration curves.